All right, welcome back. Y'all have a good spring break? Cool. I was sick most of spring break. Sucked for me. Feel sad. Not COVID though, so don't worry. All right. So don't forget, we have an exam this week. All right, it'll cover 3 chapters: the radical chapter, conjugation, resonance, and dienes, and then the first aromatics chapter. Depending on what edition you have, the chapter numbers may be a little bit different. In my book, they're 15, 16, 17. If you have the new edition, it may be 13, 14, 15. Right? So just keep that in mind. All right. If you have any questions along the way, please feel free to ask. All right. We're about to get into the next chapter, though, the next aromatics chapter. That is, in my book, chapter 18. This one is going to get into the reactivity of aromatic compounds. And this one's a pretty long chapter. This one's pretty long and involved. And you're going to see that what we can do with aromatics as far as reactivity is going to be greatly different than what we've seen with other compounds. Right? We've already seen that, if you take an aromatic compound like benzene and let's say you just wanted to do an addition reaction, right? Just like we did with alkenes, you learned that with traditional alkenes. You can take Br2, add it to the double bond, and get something like that, right? That's what we've learned in the past. However, we said this doesn't occur here. Aromatic compounds, they don't undergo addition reactions, even though they have all those pi electrons. Why not? Why do we say aromatic compounds, they don't want to be involved in addition reactions? Ooh, I'm gonna knock some of that spring break rest off.
The benzene is already stable.
What's that?
The benzene is stable.
Benzene's already very happy, right? It's already very stable. Why? Because it's aromatic, right? When we learn to be aromatic, you have to satisfy this very involved list of criteria, right? If you do an addition reaction, it's not aromatic anymore, right? In fact, in this case, we'll be converting an aromatic compound to a non-aromatic compound. It's not completely conjugated, right? So that's the reason we're not going to see addition reactions in this chapter. However, one thing that we can do, one group that we can work with is substitutions. This has its name. It's called electrophilic aromatic substitution. Or EAS for short. All right, so in EAS, if you have a benzene or benzene derivative, right, let's just use benzene. Well, all these carbons have one H attached. We usually don't draw them, right, because, skeletal structure, but they're there, right? So one thing that's easy to do is we can use some sort of electrophile, and the electrophile can come in different forms. So, I'm going to write E+ here as sort of a general notation. It's not necessarily always positively charged, though, so just kind of keep that in mind. And it's pretty easy to take an electrophile such as this and replace one of those H's. There's several different ways to do this. In fact, we're going to learn about 5 different EAS reactions. And even within some of those reactions, you can have some subclassifications. right? So it does get a little bit involved. Let me show you the general mechanism, though, for how this works. All right, let's just say we had something like that. This is a general mechanism. Again, this can vary a bit, but it's a pretty good overview. You have an electrophile, right? That's E+. What's an electrophile looking for? What does it want to interact with? Electrons. Where do we have extra electrons? Or available electrons? Yeah, a bunch of pi electrons, right? So, a pair of pi electrons from your aromatic system can interact with this positive electrophile. Create this. Okay. This pair of electrons is now being used to bond E. That means this carbon loses some electrons, so it goes positive. Is this step in and of itself a favorable step? Yes or no? I mean, it happens, right? But if this was the only thing that happened, how favorable would you think it'd be? Not very? Why not? It's not aromatic anymore, right? We're making the benzene ring less aromatic than it was, and that's not good. However, we're not done. The only reason this can happen is because we can very quickly reform the aromatic ring. Some sort of material acts as a base here, and oftentimes, whatever's acting as the base is sort of a leftover material from generation of your electrophile. All right, so your base can do what bases do. It can accept a proton from that carbon, and guess where these electrons go? They go right into the ring. And voila, creates your aromatic ring system. And now you have your aromatic ring, but with the electrophile attached instead of that other hydrogen. Okay. So if you're thinking the general mechanism of electrophilic aromatic substitution, bless you, it's basically two parts. Attraction of the electrophile to the ring, and the action of the base to reform the aromatic system. That make sense? Any questions so far? All right. So, like I said, there's several different ones that we can talk about. And they all kind of follow this general pattern. They do vary a little bit in terms of generation of the electrophile. All right. Let me list them for you real quick. All right, so we have 5 different EAS reactions. I'm going to list them real quick and then we'll go over them individually in more depth. First one is halogenation. What do you think we're putting on the ring here? Very good. Halogen. Specifically, either chlorine or bromine. All right, and so you're going to use either Cl2 or Br2 as a reagent. All right. So to do this, I'm just going to draw the resonance hybrid because I'm being lazy. We're going to take benzene. We're going to take Br2. Now, in and of itself, This is not reactive. If I just put these two reagents together, that would be an NR for no reaction. You have to have a catalyst to drive this. And that's FeBr3. I'm going to draw an alternate line here for the chlorine version because there is something notable here. You try to match the halogen in your catalyst to the halogen you're putting on the ring. So if you use Br2, use iron tribromide. If you use Cl2, use iron trichloride. And that's going to be a theme that you're going to see with all these reactions, right? You're going to have something in your reaction setup that's going to act as a source of your electrophile. In this case, like this reaction with Br2, that's the source of your electrophile. And then you see something else that's used as a catalyst. That's a running theme for all these reactions. None of them can run on their own without a catalyst, except in certain sort of selected situations, but on a general basis, it doesn't work. All right, second one's called nitration. In nitration, we're going to add two acids. First one's going to be nitric acid, HNO3. This is going to be the source of our electrophile. We're going to have an acid catalyst, sulfuric acid. This is how we put on a nitro group. All right. And we have sulfonation. In sulfonation, we're going to use SO3, sulfur trioxide, excuse me. And again, we're going to use sulfuric acid as an acid catalyst. And the purpose of this is to add something called a sulfonyl group, which is something I'm pretty sure you haven't heard of yet. A sulfonyl group is SO3H. And as we get to the mechanisms, I can draw out the full structures of these so you can kind of see exactly, you know, the electronic representation and everything. Although in usual notation, we just abbreviate them like this. These two are kind of sister reactions. They work very, very similarly to each other as far as the mechanism goes. So a lot of times, these two are kind of considered as being sort of a pair, although they are, you know, completely individual reactions. All right, 4 and 5 are named reactions. They're both called Friedel-Crafts reactions after a couple of researchers named Friedel and Crafts. And these are ways of getting particular types of carbon chains. All right, the first one's called Friedel-Crafts alkylation. And if you look at the name alkylation, that should tell you a little something. It tells you we're going to be putting an alkyl group, basically an R group, right? So what you do is you add an alkyl chloride, and you tailor the R group to be whatever you want it to be. So it could be like CH3Cl, CH3CH2Cl, et cetera, et cetera. You get the idea, right? Then you have to add a catalyst, AlCl3. Let's see our, yes?
Is it always going to be AlCl3?
Yes. Good question. Aluminum trichloride. Oh, I hate working with that stuff. It's like aluminum trichloride is like this really, really fine powder, and it's a Lewis acid. It's really reactive, and it'll actually react with the air. So when you close the bottle, there's a little bit of air that gets trapped into the bottle from the ambient surroundings. It has a little bit of water. You can actually have a little bit of reaction with the water in there, and it produces HCl gas as a byproduct. So what's really disturbing is you can get the bottle, you open it up, sometimes it'll go like a little poof, and that little poof is HCl gas that comes out. And then of course it spreads out more powder, which you can breathe in and make HCl in your lungs. That's really not a fun experience. It has happened to me before. So I'm a lot more careful now. So yeah, that was back in my student days. So you'll get to work with it later. Give you something to look forward to. It's not that bad. All right. The second one is pretty similar. It's called Friedel-Crafts acylation. All right, Friedel-Crafts acylation is a way of putting a ketone group onto a benzene ring. So instead of using an alkyl chloride, we use this. That's actually a new type of molecule. That's called an acid chloride. And again, you use AlCl3. All right, make a note here. This only makes ketones. The reason I say that is because fast forward, when we're doing synthesis problems, a lot of times, we might be doing a synthesis and you have to synthesize something that has like an aldehyde group hanging off of a benzene ring, or maybe a carboxylic acid group. So people will try to do this, and they'll put like an H, or they'll put like some crazy amalgamation of stuff. This has to be just a carbon chain, so it only makes ketones. It doesn't make anything else. If you want to have an aldehyde group hanging off of a benzene ring, there's an entirely different way to do it. If you want to have an acid group hanging off a benzene ring, entirely different way of doing it. So it only works to make ketones. All right, any questions so far? All right, that's the quick and dirty overview. Let's take a little bit more of a closer look at some of these. Let's start off with halogenation. Okay. All right, so let's try to put a BR. All right, and I'm going to draw the BR2 like that so you can see what's going on as far as the mechanism. Yes, ma'am.
Are we looking over on that first one, that halogenation?
Yes. Yeah, this is halogenation. So we got this, and we also said we have a catalyst. And the very first interaction that we have in this whole system is between your Br2 and your catalyst, right? FeBr3 is what we call a Lewis acid. You guys have heard this term before, way back in chapter 2, all right? So let's review the definition of a Lewis acid. Y'all remember? Ooh, definitions of acids and bases. What's the let's walk it back a little bit. What's the Bronsted definition of an acid? You know, these definitions involve like protons and electrons and donors and acceptors and stuff. Just got to figure out which is which. What does the Lewis definition deal with? Protons or electrons? Electrons, yeah. Lewis acids and bases, they deal with electrons. All right, so if you have a Lewis acid, what does it do with electrons? Does it accept them or does it donate them? Let's figure it out. Let's look at the structure of FeBr3. That's the structure of FeBr3. All right, look at the iron. What can you tell me about the iron and its electrons here? How many electrons does it currently have in its outer shell? What's that? I thought I heard somebody say something. How many electrons does iron currently have? What's that? 6, right. 2, 4, 6. Does iron have a full outer shell of electrons? No. Can it accept more? You betcha, right? So this is a Lewis acid. Electron pair acceptor, right? This iron can accept electrons because it doesn't have a full outer shell. And so that's what happens here. One of your bromines gets attracted to your iron, and you form a complex. All right. Iron's going to have a negative charge now because it's accepting extra electrons. The bromine that's attached to it has a positive charge. Okay? So that's the very first thing that happens in halogenation. You form a complex between your halogen and your catalyst. And this is what's going to serve as the source of your electrophile. Right? So this big whole thing is going to be sort of floating along. It's going to come along and eventually it's going to hit your aromatic ring, right? So what happens is as this whole complex gets close to the aromatic ring and these pi electrons, what's going to happen is it's going to polarize. This pair of electrons, this bond is going to break. These electrons are going to go over here to this bromine. And at the same time, pi electrons in your ring are going to grab that bromine. All happens at once. Okay. So that's how you get Br on the ring. And you also have that. So, okay. Y'all with me so far? All right. Okay, so we've gotten the electrophile on the ring, but now what do we have to do? We said there's two phases to this, right? The first is electrophile attachment. What's the second phase? You got to make it aromatic again, all right? And to do that, you need a base, right? We need a base that can pluck off an H from this carbon. For this reaction, the base is that right there, all right? That Br minus, that extra Br that's on your iron, that can come off, and that'll grab that H, and those electrons will reform the ring. So that gives you your alkyl bromide. You're going to get a byproduct here. You're going to get HBr as a byproduct. And you're going to regenerate your FeBr3. Because what do we know about catalysts? They're always regenerating. So that's a good indicator here. If you're trying to go through the mechanism of one of these, and you can't end up, and you do something and you don't end up regenerating your original catalyst, then you probably know something went wrong along the way. Okay. That is halogenation. That makes sense? Are there any questions so far? Right. So yeah, you saw this is one way to sort of generate the electrophile, right? You're going to see there's other ways as well. The next one we're going to do is nitration, and it works a little bit, it's kind of similar, but kind of different at the same time. So let's take a look at nitration. All right, we said this was the setup. All right, one similarity between this one and the last one is that the very first interaction occurs between your source of your electrophile and your acid catalyst. In this case, sulfuric acid is our acid catalyst. It's actually a Bronsted acid catalyst because it actually detonates a proton. Right? I'm going to draw out nitric acid for you. That's the structure of nitric acid. It's a weird looking molecule, right? It's what we call a Zwitter ion. Zwitter ions overall are neutral, but they have individual charged portions. Yeah, that's the structure of nitric acid. Then we have sulfuric acid over here. You know they're both strong acids, right? You probably have heard that before. You know which one's stronger? I bet you've really wondered that a lot. Sulfuric is stronger. So this is a rare case where you can see nitric acid actually acting as a base here. It can accept a proton from sulfuric acid. To give you that, and then you have HSO4 minus sitting over here out of the way. Now, when that OH accepted the proton, what did we create on the nitrogen? We had an OH on that nitrogen. Now what do we have? Water. And what do we know about water? It's a good It's a good it's a good leaving group. Yeah, it's a good leaving group. So guess what it does? It leaves. And at the same time it leaves, a pair of electrons from over here can drop down. You get that. That is your electrophile right there, NO2+. So definitely a little bit different than the last one we looked at. Bless you. Still involves interaction between the two species, but definitely a bit of a different type of electrophile. Okay. That's the drawn out version. Usually whenever we're representing this like in mechanisms or structure or anything like that, we'll just simply abbreviate it as NO2+. So you don't have to draw out the Lewis structures or anything. I just wanted to do that so you can see it. Okay. All right. We got our benzene ring. We got our NO2+. What do you think is going to happen? What's that? Yeah, you got your electrophile, right? Now, once you got your electrophile, it's just going to follow the general steps of the EAS mechanism, right? Your positive electrophile is attracted to the pi electrons. So we did that. Now, we just have to reform our aromatic ring. And to do that, we've got to have a base, something that we can get rid of that proton with. Any ideas on what we can use as the base? What can grab that proton? Yeah, don't forget the HSO4 minus. It's just sitting out here, waiting for something to do. That can come in, grab your H, electrons go in. Boom, you have your nitrobenzene. And that also allows you to regenerate your acid catalyst, your H2SO4. Excuse me. That make sense? Any questions? All right. Let's look at the third one. Let's look at sulfonation. All right, I said sulfonation was kind of similar to nitration. And a lot of that's because they both use sulfuric acid as the acid catalyst. All right, so let's take a look at this. All right, again, first thing that we're going to have is an interaction between the source of our electrophile and our acid catalyst. So we said our source of our electrophile was SO3, sulfur trioxide, and that's the structure of sulfur trioxide. Right? Sulfur trioxide is going to interact with sulfuric acid. And this interaction is actually pretty simple. It's probably a little bit simpler than the nitric acid interaction. All right, again, sulfuric acid is going to want to donate a proton. It's going to donate a proton to one of your SO pi bonds. And it's going to create this. And that is your electrophile. And commonly, we'll just abbreviate that as SO3H. Okay. Well, you can probably fill in the rest of the blanks here, maybe, hopefully. Tell me what happens. Mm-hmm. Yeah, there's a distinct pattern here. I'm trying to sort of, kind of drill it in your heads. Make that electrophile attacks the pi bond. And then you reform the ring. Lather, rinse, repeat. What's going to be the base in this case? That rhymed. I didn't mean to. HSO4. Just like the last reaction, HSO4 minus can act as the base here. So that accomplishes two things. Number one, you make your aromatic ring. And number two, you reform or regenerate your catalyst. Okay. Does that make sense? Any questions? Cool. All right. Now, the two we got left were the Friedel-Crafts reactions. I know I listed them in a certain order. I think I put alkylation first and acylation second. I'm actually going to go over Friedel-Crafts acylation first because it's simpler. We'll see that Friedel-Crafts alkylation is a little quirky. So let's do this one first. Friedel-Crafts acylation. So let's say we had benzene, and let's just say you wanted to put a methyl ketone on there, so we'll just use that acid chloride, AlCl3. Right? Okay, so hopefully you can sort of recognize the pattern here. First thing that happens is you have interaction between your catalyst and the source of your electrophile. All right, so these two guys are going to interact. This is going to be fairly similar to what we saw with halogenation, but with a little bit of a twist. All right. So let's say we have this. We have this. All right. Now, what do you notice about aluminum here? It's a Lewis acid, yeah. Just like with iron in the previous example, aluminum can accept electrons. And there's an abundance of them on this chlorine, right? So in the halogenation, you saw that you formed the complex, right? It's going to be a little bit different here. In this case, the Cl will actually just go ahead and detach itself and completely hop over to that aluminum. And leave a positive carbon behind. and AlCl4 minus. So no complex in this case, it just completely leaves the carbon behind. The reason is this is resonance stabilized, so it's really easy to form, and it can exist on its own. And this just happens to be your electrophile. Okay? So, from here on out, it looks just like any other EAS reaction, right? Electrophile attaches to your benzene ring. All right, we got to have a base in order to pluck off hydrogen. What do you think the base is here, based off of previous examples? Yeah, you still got that AlCl4 sitting out there. Now, we saw a similar example with halogenation, right? This follows the same path. That extra Cl minus will come off. It'll grab that H. And that will reform the ring. You'll form HCl as a byproduct. And you end up reforming the AlCl3. So Friedel-Crafts acylation is pretty similar to halogenation, with a slight difference at the beginning. Okay. That makes sense? Are there any questions so far? All right. All right, let's talk about Friedel-Crafts alkylation. And like I said, Friedel-Crafts alkylation is a little bit quirky. There's a little bit more to it than some of the other ones. All right, you know in Friedel-Crafts alkylation, you have benzene, then you have an alkyl chloride of some sort. Something like CH3Cl would be an example. And then also AlCl3. Now, how this works is a little bit different depending on the type of alkyl chloride you have. What I'm about to show you works with methyl chloride and primary alkyl halides only. The process for secondary and tertiary alkyl halides is different. This is pretty much spot on analogous with halogenation. It works basically the same way. You got this. You got your Lewis acid catalyst. What happened in halogenation? What did we form? What do we do in halogenation? Interaction between your electrophile and your catalyst. Yeah, we formed a complex, right? Because halogen could donate electrons to your iron in that case. In this case, basically the same thing. You can form a complex through sharing of that electron pair from this chlorine. So you form that. Right. So you've got that complex, you've got your benzene ring. Well, based off of the halogenation reaction, what do you think happens? You can use it as a model for this one. It works the same way. Yeah. This is kind of polarized as you get closer to the pi electrons. This pair of electrons will go over to this chlorine, and at the same time, this CH3 will attach to your benzene ring. And just like we've seen a couple of times already, this species right over here can act as your base. This Cl minus will detach, grab that H, reform the ring, and viola, you've got your product. So you got a methyl group on your ring now, got HCl as a byproduct, and you reform the catalyst. You guys draw that. Yeah, perfectly analogous to halogenation. The only difference is, in this case, the species on the other side of your halogen is a CH3 instead of another Cl. And the fact we're using an aluminum-based catalyst instead of an iron-based. But the mechanism works exactly the same. Yeah? That makes sense? Any questions? All right. Now, let's check it out for secondary and tertiaries because it's going to be a little bit different. Similar, but definitely different. All right, let's say we got this. That's a secondary alkyl halide. All right, so let's see how this works. Just like any other reaction of this type, you're going to have interaction between your alkyl chloride and your catalyst. Okay. All right. We saw the previous mechanism was analogous to halogenation, right? This one, however, is analogous to Friedel-Crafts acylation. What happened in Friedel-Crafts acylation? Chlorine just goes. Yeah, and that's what happens here. It completely hops over. The reason it can do that is because when it does so, it makes a stable carbocation. It'll make either a secondary or a tertiary carbocation, depending on what structure you have. You couldn't do this with CH3Cl, right? Because in that case, it would produce a very unstable carbocation. So that's why the primaries and methyl chlorides don't do this. But if you can form a secondary or tertiary, then it's just fine. Right? From there on out, it's business as usual. You get attachment of the nucleophile. Your Cl minus detaches from AlCl3. Grab this proton, reform the ring, doobie doobie doo. And you've got your isopropyl benzene. HCl is a byproduct, and you've regenerated your catalyst. As Ace Ventura used to say, BEA beautiful. Does anybody know who Ace Ventura is? Oh, good, you do. Okay. You guys seen his movies? Never in 1,000 years did I think I'd be making an Ace Ventura reference this morning, but hey, you never know what's going to happen. All right, we are about out of time. Are there any questions about anything we've gone over today? All right. You studying for your exam? No quiz this week. I'll let you guys just focus on your exam. If you have any questions at any point, again, just let me know. Oh, we already did. We're not, this is not on the exam, or not on this exam anyway. The exam is over the free radical chapter, the conjugation, resonance, and dienes chapter, and then the first aromatic chapter, where we talk about aromatic, anti-aromatic, non-aromatic, all that stuff.
So like the molecular bonding period would still be on.
Yeah. This stuff will be exam 3 stuff. All right. Have a good one.